May 19th, 1943. Telefunken Research Laboratories, Berlin. Dr. Wilhelm Runge placed the captured American SCR-5-eight-four radar set on the examination table with hands that trembled slightly. Around him, Germany's finest radio engineers, men who had pioneered radar development in the 1930s, waited in silence. The device had been recovered from a downed B-17 over Wilhelmshaven 2 weeks earlier, remarkably intact. Runge had spent 14 days studying its exterior, measuring its dimensions, calculating its probable capabilities based on antenna size and presumed wavelength. Every calculation suggested this was standard Allied radar, probably inferior to German Wurzburg systems. Now, as he prepared to open the casing, Runge felt the confidence of a man about to confirm his nation's technological superiority. What he found inside would shatter that confidence within minutes and force German military science to confront a devastating truth. American radar technology wasn't slightly ahead, it was years beyond anything German laboratories had conceived possible. The revelation would cascade through every level of German military planning, exposing fatal assumptions about Allied capabilities and German ingenuity. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story begins not with the capture, but with the confidence. In 1940, German scientists had reason to believe they led the world in radar development. The Wurzburg radar system, operational since 1940, could detect aircraft at 60 miles and guide flak batteries with unprecedented accuracy. German night fighters used Liechtenstein radar to hunt British bombers in darkness. The technology seemed adequate, even superior. German intelligence reports from 1941 and 1942 suggested Allied radar lagged behind German systems. British chain home stations used crude, long-wavelength radar that German engineers dismissed as primitive. American radar, to the extent Germans knew about it, appeared to follow British designs, with typical American emphasis on mass production over sophistication. This assessment permeated every level of German military thinking. At technical conferences, scientists spoke confidently of German leadership in radio physics. In planning meetings, officers assumed radar parity or German advantage. Field commanders operated under the belief that Allied electronic warfare capabilities matched or fell short of German systems. This wasn't arrogance alone. It was analysis based on the best available intelligence, interpreted through the lens of German scientific achievement. German radar development had followed a logical path rooted in solid physics and careful engineering. In 1934, Rudolf Kuhnhold had demonstrated the first practical German radar system. By 1938, the Kriegsmarine employed SeaTac naval radar. The Luftwaffe's Freya early warning radar became operational in 1939, detecting aircraft at 75 miles. Each system represented incremental improvement, careful refinement of established principles. German engineers understood radio physics intimately. They had pioneered radio communication, developed sophisticated receivers, and created precision measurement instruments. When they examined captured British radar in 1940, they found exactly what they expected: large antennas, long wavelengths, adequate but unimpressive performance. The technology confirmed German assessments. Allies possessed functional radar but had not revolutionized the field. German scientists continued their methodical development, improving existing systems through better components and refined designs. The Wurzburg underwent several upgrades, increasing range and accuracy. Liechtenstein radar improved enough to make German night fighters effective predators. These were solid achievements that any engineering program would celebrate. But they were evolutionary, not revolutionary. The German approach to radar emphasized precision engineering and careful frequency selection. Operating primarily in the high-frequency and very high-frequency bands, German radar used wavelengths of 1 to 2 meters. These frequencies offered good range and reasonable accuracy with manageable antenna sizes. The technology was mature, well understood, and reliable. Component production was established, with German manufacturers capable of producing radar sets in substantial numbers. The entire system, from research laboratories to frontline operators, functioned with German efficiency. Scientists developed specifications, engineers built to those specifications, and military units deployed the equipment effectively. It was exactly how technological development should work in a well-organized military power. German confidence in this approach seemed justified by results. Wurzburg guided flak batteries to accuracy rates that impressed even Allied bomber crews. Freya provided early warning that allowed Luftwaffe fighters to intercept raids effectively. Naval radar helped surface vessels and U-boats detect threats and targets. The systems worked. They fulfilled their intended functions. What more could be asked? In late 1942, intelligence reports began suggesting something unexpected about Allied electronics. German signals intelligence intercepted radio transmissions from Allied aircraft that seemed to indicate new radar systems. The signals operated at frequencies German receivers sometimes missed entirely. Luftwaffe pilots reported that Allied bombers appeared to detect German night fighters before interception, suggesting airborne radar of unexpected capability. U-boat commanders noted that Allied aircraft seemed to locate submarines with uncanny accuracy, even in poor visibility. These reports troubled German technical intelligence officers, but explanations seemed available. Perhaps the Allies had simply increased the number of radar sets, achieving better coverage through quantity rather than quality. Perhaps better training and tactics explained improved performance. Perhaps German intelligence was overestimating Allied capabilities based on incomplete data. The possibility that Allied radar had fundamentally leaped ahead seemed unlikely. Such advances required breakthroughs in basic physics or revolutionary component development. German scientists monitored international physics journals and tracked Allied research through intelligence networks. Nothing suggested the Allies had achieved anything beyond incremental improvements to existing radar technology. The capture of the SCR-584 changed everything. The circumstances were almost routine. On May 5, 1943, a B-17 from the 91st Bomb Group sustained flak damage over Wilhelmshaven. The crew managed to keep the aircraft airborne for 30 miles before crash landing in a field. German troops reached the wreckage quickly enough to prevent effective destruction. Among the equipment recovered was the aircraft's radar set used for navigation and bombing through clouds. Standard procedure required shipping captured equipment to technical intelligence for examination. The SCR-584 arrived at Telefunken laboratories on May 7th. Initial external examination revealed nothing alarming. The unit was compact, well-constructed, and appeared to be standard airborne radar. German engineers estimated it operated somewhere in the very high-frequency band, similar to German systems. The external antenna suggested wavelengths consistent with German radar theory. Everything indicated this would be a routine examination, confirming that American radar followed expected patterns, perhaps with interesting detail differences, but no fundamental surprises. Dr. Wilhelm Runge, at 43 years old, was among Germany's most accomplished radar engineers. He had contributed to Wurzburg development, authored papers on radio propagation, and earned respect throughout German technical circles. His assessment of captured Allied equipment carried significant weight. When Runge began his preliminary examination of the SCR-584, he worked with the confidence of expertise. He measured dimensions, calculated probable frequency ranges, and estimated performance based on antenna characteristics. His initial report, filed on May 10th, concluded that the device represented competent American engineering, but showed no revolutionary advances. It was the kind of professional assessment German military planners wanted to hear. Allied radar remained comprehensible, manageable, and within German ability to match or counter. Runge scheduled the internal examination for May 19th, allowing time for proper documentation and assembly of appropriate colleagues. 7 other senior engineers would attend, ensuring comprehensive analysis. The examination room at Telefunken on the morning of May 19th held some of Germany's finest electronic warfare talent. Dr. Hans Plendl, who had developed much of the Luftwaffe's radio navigation technology, stood beside Runge. Engineer Ernst Kramer, specialist in radio frequency components, prepared measuring instruments. Major Ludwig von Alvensleben represented military technical intelligence, ready to assess operational implications. 4 additional engineers, each with specific expertise in transmitters, receivers, antennas, or power supplies, completed the team. They gathered around the examination table where the SCR-5-eight-four sat under bright lights, still sealed in its protective casing. Runge addressed the group briefly, outlining expected findings and examination procedures. The mood was professional, even slightly routine. They were about to examine enemy technology, but nothing suggested this examination would differ from dozens they had conducted previously. Runge picked up a screwdriver and began removing the access panels. What he revealed in the next 30 minutes would force every person in that room to question fundamental assumptions about German technological leadership. The first shock came immediately. Removing the main access panel exposed the radar's internal cavity magnetron, the component that generated radio frequency energy. German engineers knew about cavity magnetrons. The principle had been understood since the 1920s, but creating a high-power magnetron that operated reliably at very short wavelengths was extraordinarily difficult. German researchers had struggled for years to build magnetrons that produced more than a few watts at wavelengths below 50 centimeters. The British had achieved some success, German intelligence knew, but nothing suggested revolutionary progress. The magnetron, sitting in the American radar set, was operating at wavelengths German engineers initially couldn't believe. Runge's first measurement with a frequency meter showed wavelength of approximately 10 centimeters. He repeated the measurement 3 times, certain the instrument was malfunctioning. 10 centimeters was the microwave territory, a frequency range German radar had barely explored. At that wavelength, the tiny magnetron in the American set would need to generate kilowatts of power. That seemed physically impossible with 1940s technology. Yet, the evidence was undeniable. The magnetron was smaller than a German's hand, weighed perhaps 2 pounds, and somehow produced microwave radar signals. Plendl examined the magnetron closely, his face reflecting growing concern. He understood immediately what this meant. Microwave radar offered extraordinary advantages: smaller antennas for equivalent beam width, better target resolution, reduced interference, and potential capabilities German systems couldn't match. If the Americans had mastered high-power microwave generation, they possessed technology Germany had believed impossible. The implications extended far beyond this single radar set. Microwave technology would enable entirely new classes of radar systems, from precise bombing aids to compact airborne intercept radars to proximity fuses for anti-aircraft shells. Everything German electronic warfare doctrine assumed about Allied capabilities required immediate revision. Kramer carefully removed the magnetron from its mounting, handling it with the reverence due to a revolutionary artifact. The component's construction revealed sophisticated understanding of microwave physics. Resonant cavities precisely machined, cooling fins carefully designed, output coupling optimized for maximum efficiency. This wasn't crude experimental equipment. This was production hardware built in quantity, deployed operationally. The Americans hadn't just achieved a laboratory breakthrough. They had industrialized microwave technology. The examination continued with mounting disbelief. The radar's receiver used components German engineers had never seen in operational equipment: miniaturized vacuum tubes, later identified as American-developed sub-miniature tubes, packed functionality into impossibly small spaces. German radar used standard radio tubes, large and power-hungry. The American tubes were a fraction of the size, enabling compact designs German engineers had thought impractical. The circuit design itself reflected sophistication that impressed even skeptical German minds. Automatic frequency control maintained precise tuning. Sensitivity time control reduced clutter from nearby objects. Discriminator circuits rejected false signals. Each feature represented careful engineering and deep understanding of radar theory, but the overall integration showed something more remarkable. The Americans had created a system where every component worked in harmony, maximizing performance while minimizing size and weight. German radar, by comparison, seemed crude and cumbersome. It worked, certainly, but with brute force rather than elegance. Major von Wilhelmshaven watched the examination with military eyes, calculating operational implications. If one American bomber carried radar this sophisticated, how many did they have? If this represented standard equipment, what did their advanced systems look like? The questions multiplied faster than answers emerged. German night fighter tactics assumed Allied bombers had limited ability to detect fighters approaching from behind. That assumption now seemed dangerously wrong. German U-boat doctrine relied partly on surface operations that microwave radar would make suicidal. That doctrine needed immediate reconsideration. German flak defenses assumed they could detect incoming bombers at roughly the same range bombers could detect targets. That parity no longer existed if Allied aircraft carried radar this capable. Von Wilhelmshaven excused himself after 90 minutes, rushing to telephone Berlin. His commander, General Wolfgang Martini, head of Luftwaffe signals and communications, needed to know immediately that German electronic warfare strategy rested on false foundations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By noon, the examination team had catalogued enough evidence to draft preliminary conclusions, but Runge insisted on thorough analysis before making official reports. The radar's modulator, which controlled timing and pulse characteristics, showed advanced design concepts. The power supply operated with efficiency German engineers struggled to achieve. The antenna feed system used waveguide technology German laboratories had barely begun exploring. Even the mechanical construction impressed. Aluminum casting created complex shapes with minimum weight. Fasteners used quick-release designs for field maintenance. Every aspect of the radar reflected a development philosophy fundamentally different from German approaches. Where German engineers optimized individual components, Americans had optimized the entire system. Where Germans pursued technical perfection, Americans achieved practical excellence. The difference seemed subtle, but proved profound. German radar worked beautifully in laboratories and adequately in field conditions. American radar, judging from this example, worked excellently under operational stress. That margin of practical superiority could determine victory or defeat in electronic warfare. The most disturbing discovery came late in the afternoon when engineers examined the radar's documentation, recovered separately from the crash site. American technical manuals accompanied operational equipment, a practice Germans rarely followed so thoroughly. The SCR-5-eight-four manual was comprehensive, clearly written, and revealed something shocking. This radar wasn't cutting-edge American technology. It was standard production equipment, manufactured in thousands, deployed throughout bomber and transport fleets. The manual's date stamp showed revisions from 1942, meaning this technology had been operational for at least a year, probably longer. If this represented routine American radar, what did their advanced systems achieve? German intelligence had completely missed the magnitude of Allied radar development. Years of careful monitoring, espionage, and technical analysis had failed to detect that American radar had leaped an entire generation ahead. The failure wasn't merely embarrassing. It was operationally catastrophic. German air defenses, German naval tactics, German electronic warfare, all were planned against enemies using technology Germany now realized was obsolete by American standards. Fighting with this intelligence gap was like entering battle blind. Dr. Plendl spent the evening calculating what microwave radar meant for Luftwaffe operations. German night fighters relied on Liechtenstein radar operating at 65 centimeters wavelength. Allied bombers could detect Liechtenstein emissions from miles away using simple receivers, essentially seeing German fighters coming. But microwave radar operating at 10 centimeters would be much harder to detect, giving Americans decisive advantage in airborne interception. German radar warning receivers, designed to detect British chain home frequencies, would miss microwave signals entirely. If Americans deployed microwave radar widely, German aircraft would be electronically blind, while Americans saw everything. The situation was worse for German naval operations. U-boats surfaced at night, believing darkness provided protection. British radar had already compromised that tactic, but German U-boat command assumed submarines could still operate on surface in many conditions. Microwave radar from Allied patrol aircraft would detect surfaced U-boats with near certainty in any weather, day or night. The submarine warfare, on which Germany staked so much, had become potentially suicidal. Admiral Karl Dönitz, commanding U-boat forces, would need to know immediately. Runge worked through the night, drafting his official report. The document would become one of the most consequential technical assessments of the war. His conclusion was stark and unambiguous. The captured American radar represented technology Germany could not quickly match. The magnetron alone required manufacturing capabilities German industry didn't possess. Even if German laboratories duplicated the design immediately, which would take months minimum, production would require retooling, specialized materials, and testing that would consume a year or more. By then, Americans would have advanced further. Germany had lost the radar race and lacked the resources to catch up while simultaneously fighting on multiple fronts. Runge's recommendation shook German military confidence. Germany should assume American radar superiority across all operational domains and modify tactics accordingly. Attempts to match American technology would fail unless given absolute priority, which war conditions made impossible. The only realistic response was defensive. Develop countermeasures, change tactics to minimize radar's advantage, and accept that Germany would fight electronically disadvantaged for the foreseeable future. The report reached Reichsmarschall Hermann Göring's headquarters on May 22nd. Göring, whose Luftwaffe bore responsibility for air defense and electronic warfare, read it with visible anger. The assessment contradicted everything German propaganda claimed about Aryan scientific superiority. It suggested Americans, whom German ideology dismissed as culturally inferior, had achieved technological breakthroughs German genius couldn't match. Göring demanded verification, ordering additional experts to examine the radar and confirm or refute Runge's conclusions. Over the next week, 3 separate teams evaluated the SCR-584. All reached identical conclusions. American microwave radar represented a genuine technological revolution Germany had missed entirely. The implications were staggering and undeniable. On May 30th, 1943, German military technical intelligence issued a classified report titled Assessment of Allied Radar Capabilities Based on Captured American Equipment. The document, distributed to fewer than 50 officers, painted a picture of Allied electronic superiority that contradicted years of German assumptions. American radar operated at wavelengths German systems couldn't match. American magnetrons produced power levels German technology approached only in laboratory conditions. American radar sets integrated sophistication, miniaturization, and reliability that German equipment didn't achieve. Most critically, American radar production apparently numbered in the tens of thousands of units, while German radar production counted in the hundreds. The industrial scale of American electronics manufacturing overwhelmed any German technological advantages that might have existed. The classified report of May 30th, 1943, triggered a crisis in German military planning that reverberated through every branch of the Wehrmacht. Within 48 hours, emergency conferences convened in Berlin, bringing together radar specialists, operational commanders, and intelligence officers. The mood was grim. General Wolfgang Martini, addressing Luftwaffe technical staff on June 2nd, stated what everyone in the room understood, but few wanted to acknowledge. We have been operating under a dangerous delusion. American radar isn't merely adequate, it's superior to ours in fundamental ways we cannot quickly remedy. Our tactics, our defensive planning, our assumptions about Allied capabilities all require immediate revision. The psychological impact of this admission cannot be overstated. German military culture prided itself on technological sophistication and scientific achievement. The revelation that Americans had quietly surpassed German electronics research struck at the foundation of that pride. It forced uncomfortable questions. If German intelligence had missed American radar developments so completely, what else had they missed? If American industry could mass-produce sophisticated microwave systems, while Germany struggled to manufacture basic radar sets in adequate numbers, what did that reveal about relative industrial capacity? These questions had no comfortable answers. Field units received the news through carefully worded technical bulletins that understated the situation's severity. Luftwaffe night fighter squadrons learned that Allied bombers might possess detection capabilities exceeding German radar range. U-boat commanders were warned that Allied patrol aircraft could detect surface submarines with greater accuracy than previously estimated. Anti-aircraft batteries received instructions to assume Allied bombers could navigate and bomb effectively through clouds regardless of visibility. Each bulletin chipped away at German tactical confidence without explicitly stating the core problem. Germany was fighting electronically blind against enemies who could see clearly. The Kriegsmarine responded with particular urgency because U-boat warfare remained Germany's primary offensive capability against Britain. Admiral Dönitz, confronting the reality that microwave radar made surface operations increasingly suicidal, ordered immediate tactical changes. U-boats would remain submerged longer, surface only when absolutely necessary for battery charging, and dive immediately upon any aircraft detection. These measures reduced operational efficiency significantly. Submarines running, submerged, traveled at a fraction of surface speed, limiting their ability to reach patrol stations or intercept convoys. Battery life became a constant concern. Most critically, the changes acknowledged what German naval doctrine had denied. The Atlantic was no longer a domain where U-boats could operate with relative freedom. Allied technology had transformed it into a hunting ground where submarines were prey. The Luftwaffe faced equally difficult adaptations. German night fighters had achieved considerable success in 1942 and early 1943 by intercepting British bomber streams using ground-controlled guidance and airborne Liechtenstein radar. If Allied bombers now carried sophisticated radar that detected German fighters approaching, the entire system required rethinking. Luftwaffe technical staff explored countermeasures frantically. They developed new tactics, emphasizing attacks from directions Allied radar might not cover well. They experimented with radar-absorbent coatings to reduce German aircraft's radar signature. They rushed development of radar warning receivers tuned to detect microwave frequencies. Each measure helped marginally, but none addressed the fundamental problem. German night fighters were using 1940 technology against 1943 Allied electronics. The gap was too wide for tactics alone to bridge. By autumn 1943, German night fighter losses had increased substantially. Allied bomber crews equipped with tail-warning radar and increasingly sophisticated electronic countermeasures detected German fighters earlier and evaded more successfully. The kill ratio that had favored German night fighters began shifting toward parity, then toward Allied advantage. Luftwaffe pilots, men of extraordinary courage and skill, found themselves dying, not from inferior flying ability, but from inferior technology they couldn't overcome through valor alone. The human cost of German technological overconfidence became tragically apparent through individual stories that official reports reduced to statistics. Oberleutnant Werner Barker, a night fighter pilot with 17 confirmed kills, died over Hamburg on July 27, 1943. His aircraft was intercepted by an RAF Mosquito equipped with AI Mark 8 radar, a British microwave system similar to the American SCR-5-eight-four. Bake never saw the Mosquito coming. His wingman reported that Bach's Messerschmitt Bf-110 simply exploded without warning or evasive maneuver. The Mosquito's radar had provided detection and tracking that Bach's own Liechtenstein couldn't match. The irony was sharp. Bach had been an advocate for better German radar, writing reports after his 15th kill requesting improved detection equipment. His requests moved slowly through Luftwaffe bureaucracy, while British and American radar development accelerated. By the time German technical staff read Bach's recommendations seriously, he was dead, killed by the very technological gap he had warned about. His story multiplied hundreds of times across German forces, skilled men dying because their equipment couldn't match enemy systems. At sea, U-boat crews paid with their lives for German radar intelligence failures. In August 1943, U-664, commanded by Kapitänleutnant Adolf Greif, surfaced in the North Atlantic to recharge batteries. The night was dark, visibility poor, conditions that had once provided reasonable safety. An American B-24 Liberator, operating from Iceland and equipped with ASV Mark III microwave radar, detected the surfaced submarine from 18 miles. The U-boat's radar detector, designed to detect earlier Allied radar wavelengths, gave no warning. The Liberator attacked from darkness, dropping depth charges that bracketed U-664 perfectly. Greif and his entire crew of 48 men died in the attack. They never knew what detected them, never received warning, never had opportunity to dive. The engagement was utterly one-sided, made possible by American radar technology German intelligence had failed to anticipate. Admiral Dönitz, reading the patrol reports and loss statistics, understood the bitter mathematics. U-boats were being sunk faster than shipyards could replace them. The rate of loss had become unsustainable. American microwave radar, deployed on patrol aircraft throughout the Atlantic, had transformed submarine warfare from a viable strategy into a form of slow, organizational suicide. German scientists worked desperately to close the radar gap, but the effort revealed how thoroughly American electronics had surpassed German capabilities. Dr. Runge, tasked with leading German microwave radar development, reported in September 1943 that duplicating the American magnetron would require at least 18 months of development, even with the captured example to study. German vacuum tube manufacturing lacked the precision equipment necessary. German metallurgy couldn't produce the specialized alloys American magnetrons used. German testing facilities weren't configured for microwave frequencies. Each obstacle could be overcome individually, but the cumulative challenge was immense. More problematic, captured American documents and interrogated aircrews revealed that the SCR-5-eight-four wasn't even Americans' most advanced radar. Newer systems, with better performance, were already entering service. By the time Germany matched 1943 American technology, Americans would have advanced to 1945 standards. The race was unwinnable. Without resources Germany simply didn't possess while fighting on multiple fronts. The psychological impact extended beyond technical circles into German military leadership at the highest levels. Albert Speer, Minister of Armaments and War Production, reviewed radar production statistics in November 1943 and found the comparison with Allied output devastating. German factories produced approximately 300 radar sets monthly across all types. American factories, according to intelligence estimates, produced 5,000 radar sets monthly. British production added perhaps 2,000 more. The sevenfold production disparity meant that even if German radar matched Allied quality, which it demonstrably didn't, Germany would still be overwhelmed by Allied quantity. Speer's report to Hitler on November 15, 1943, contained unusually blunt language. We cannot match Allied electronics production with current resources. American industry operates at scales we cannot comprehend, producing sophisticated equipment in quantities we cannot hope to achieve. This isn't a gap that better management or increased effort can close. It reflects fundamental differences in industrial capacity. Hitler, characteristically, rejected the pessimistic assessment and demanded redoubled efforts. But Speer's analysis was accurate. Germany was fighting an industrial war it couldn't win. The captured SCR-5-eight-four sat in a Berlin technical museum where German engineers studied it throughout 1944, each examination revealing new sophistication. The radar became a symbol of German intelligence failure and American technological achievement. Young German engineering students, drafted into crash programs to develop countermeasures, looked at the American magnetron with mixture of professional admiration and national despair. The device represented everything German propaganda claimed was impossible. Americans were supposed to be practical but unsophisticated, capable of mass production but not innovation. The magnetron proved otherwise. It was innovative, sophisticated, beautifully engineered, and mass-produced in staggering quantities. Every German assumption about American capabilities was wrong. The revelation forced uncomfortable self-examination. Had German racial ideology blinded scientists to reality? Had overconfidence in German technical superiority caused complacency? Had focusing on incremental improvements caused missing revolutionary developments? These questions circulated quietly among German engineers who could see the war's trajectory and understood that technology had contributed significantly to Allied victory. By early 1944, German radar defenses had adapted as well as circumstances permitted, but adaptation meant accepting permanent inferiority. The Luftwaffe deployed new radar systems with better range and frequency agility, but they still operated primarily at wavelengths longer than Allied microwave systems. German naval radar improved incrementally, but U-boats remained vulnerable to Allied patrol aircraft equipped with microwave detection. German ground-based radar provided adequate early warning, but Allied electronic countermeasures, jamming and deception, exploited known German frequencies effectively. Every German improvement met Allied counter-improvement. The electronic warfare spiral favored the side with superior technology and greater production capacity. That side was definitively Allied. German forces fought courageously with inferior equipment, achieving tactical successes through skill and determination. But tactical excellence couldn't overcome strategic technological disadvantage indefinitely. The cumulative effect of radar inferiority showed in statistics. German aircraft losses increased, U-boat sinkings accelerated, Allied bombing accuracy improved. Each trend reflected partly the radar gap that German intelligence had failed to detect until too late. The invasion of Normandy in June 1944 demonstrated comprehensively how technological disadvantage translated to battlefield defeat. Allied forces used radar for naval navigation, aircraft coordination, artillery spotting, and battlefield surveillance with sophistication German forces couldn't match. American SCR-5-eight-four radars, the same type Runge had examined 13 months earlier, guided Allied bombers through clouds to strike German positions with accuracy that surprised Wehrmacht commanders. Allied ships bombarded German coastal defenses using radar fire control that enabled precision Germans couldn't counter. Allied aircraft used airborne radar to detect German movements and coordinate attacks in real time. The Battle of Normandy wasn't decided by radar alone, obviously. Allied numerical and material superiority were overwhelming regardless of electronics, but radar magnified that superiority, giving Allied forces information dominance that German commanders found impossible to overcome. Field reports from Normandy described German units being attacked from unexpected directions by forces they hadn't detected, being bombarded accurately through fog and smoke, being tracked continuously without seeing their observers. It was warfare, as German doctrine had never anticipated, enabled by technology German intelligence had underestimated catastrophically. In September 1944, Dr. Runge met with former colleagues at a technical conference in Dresden. The mood was somber. Germany was losing the war on every front, cities were being bombed into rubble, and the technological gap with the Allies had widened rather than narrowed. Runge, who had examined the first captured American microwave radar 16 months earlier, spoke candidly about lessons learned. We assumed American radar would follow European development patterns because we couldn't imagine they would leapfrog entire technological generations. That failure of imagination cost us dearly. The Americans didn't just improve existing radar, they revolutionized it, investing in high-risk technologies we dismissed as impractical. They succeeded because they could afford to fail, attempting multiple approaches simultaneously while we pursued single optimized solutions. His audience, fellow engineers facing defeat, understood the broader implication. German technical methodology, emphasizing careful incremental improvement and optimization, had been surpassed by American willingness to embrace risk, invest massively in parallel development programs, and accept short-term failures for long-term breakthroughs. The captured radar represented not just a device, but a fundamentally different approach to technological innovation. The war ended in May 1945 with German radar still inferior to Allied systems across virtually every category. Post-war interrogations of German engineers revealed the full extent of technological disparity. American and British technical intelligence officers interviewed hundreds of German specialists, documenting what they had known, when they learned it, and why German countermeasures had failed. The interviews produced consistent themes. German scientists had underestimated Allied willingness to invest in speculative technologies. German intelligence had focused on known Allied capabilities rather than potential breakthrough developments. German industry lacked the flexibility to respond quickly when breakthroughs occurred. German military doctrine had been slow to adapt when technology invalidated existing assumptions. Each factor contributed to the radar gap, and similar gaps existed in other technologies. Proximity fuses, advanced computing, nuclear physics. Germany had lagged or missed critical developments across multiple fields. The pattern suggested systemic problems with German technical intelligence and development philosophy rather than isolated failures. Dr. Wilhelm Runge survived the war and worked briefly for Allied technical intelligence, helping American and British engineers understand German radar development. In a 1946 interview, he reflected on the captured SCR-584 with perspective that defeat had provided. When I opened that radar casing in May 1943, I expected confirmation that German technology remained superior, or at least equivalent. What I found destroyed that comfortable assumption. The magnetron alone proved Americans had achieved what we thought impossible. That moment changed my understanding of the war. I realized we were fighting enemies who could innovate faster, produce more efficiently, and adapt more quickly than we could. Technology became destiny. The side that mastered it fastest won. His assessment echoed conclusions reached by many German officers and scientists. Technology hadn't guaranteed Allied victory alone, but it had made German victory impossible regardless of tactical skill or strategic brilliance. The radar gap, like gaps in other technologies, reflected deeper disparities in industrial capacity, scientific freedom, and innovative culture that totalitarian Germany couldn't match. The captured radar eventually found its way to the Smithsonian Institution's collections, an artifact of technological warfare and intelligence failure. It sits preserved as reminder of assumptions' dangers and humility's importance in assessing adversaries. The device itself is unremarkable to modernize, primitive vacuum tube technology that contemporary smartphones exceed in every specification. But in its historical context, it represented revolution. It embodied American innovation that German intelligence dismissed as impossible until confronted with undeniable physical evidence. The engineers who examined it learned lessons that extended far beyond radar technology. They learned that ideological assumptions about racial or national superiority cloud technical judgment fatally. They learned that dismissing adversaries as unsophisticated leads to catastrophic intelligence failures. They learned that war tests not just courage or tactics, but industrial capacity and innovative capability. These lessons, purchased at cost measured in hundreds of thousands of lives, remain relevant to any nation confronting technological competition. The story of German engineers confronting American radar superiority illuminates warfare's human dimension beyond battles and campaigns. It shows how intelligence failures kill soldiers who deserve better, how technological overconfidence breeds strategic disaster, how assumptions unexamined become lethal when tested by reality. The German engineers who examined that radar were skilled, educated, patriotic men doing their professional best. They failed not from incompetence, but from operating within a system that couldn't imagine Americans achieving technological breakthroughs German genius hadn't conceived. That failure of imagination, multiplied across German military and political leadership, contributed substantially to Germany's defeat. The radar wasn't just a device. It was mirror-reflecting truths German ideology preferred to deny. Americans could innovate. American industry could produce quality and quantity simultaneously. American military could integrate sophisticated technology into effective operational doctrine. Truth contradicted Nazi propaganda, and each proved correct when tested in warfare's ultimate arbitration. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.